The stage is yours.
Thank you. I might want to start it. Right, instead of my last. That's always a good idea. So, yeah, thank you everybody for coming to listen to me again. I'm very happy to be able to speak about another thing that I'd like to rant about, which is Jose. Who has an idea what I mean with Jose? One hand. Very, very good. Jose is basically a collection of standards of things we use in our daily lives, and it's an abbreviation for the JSON Object Signing and Encryption Standard. And when I ask, who's ever heard of JSON Web Tokens before? I see way more hands. JSON Web Tokens are a part of the Jose spec, together with some other specifications next to them. And that whole group of specifications is called Jose. But before I can dive into Jose, I would like to go through the basics of cryptography. And don't be afraid, pronouncing the word cryptography is the most difficult part of this presentation. You'll hear me struggle a lot with that, together with some other fancy words. But we're going to see the basics of certain cryptography principles, and then we're going to move on to the actual Jose specification, see what's in there, see how these things like JSON Web Tokens and other work, and hopefully by the end of this talk, you all know what Jose is about. Let's see if my clicker works. Yep, my name is still Bellen. I'm still a developer advocate at Auth0. I'm still a Google developer expert, and you can always find me at @Sambega on the internet. And my slides are available at jose.sambega.tech. So if you'd like to follow along on your phone or your devices at home, on your laptops, feel free to go to this link now or anytime after this talk. A small disclaimer. I might simplify certain things in order to try to explain them in an easier way. Cryptography gets difficult really, really fast. And I'm only going to stay on the surface level of cryptography in this talk. I'm not going to go really deep. I will try to make it as simple as possible so we all have at least a simple understanding of these principles. Also, don't reinvent the wheel. Use what's out there to deal with cryptography. There's many, many great libraries out there that have been made by experts, people who actually know what they're doing. I am not one of those. I just like to talk about it. But these libraries actually work, and they do that in a really good way. Cool. So what we're going to be looking at, we're going to look at hashing and keyed hashing, signing, encryption, and lastly, Jose, the specification in itself. So let's get started. Hashing. A hashing algorithm is a mathematical algorithm that maps data of an arbitrary size to a bit string of a fixed size. A lot of fancy words to say that no matter the length of the input, the size of the input, the output will always have the same size depending on the algorithm. For example, the SHA-256 algorithm will always have a 256-bit outcome, no matter if you put in one word, a few numbers, or a file that's a gigabyte large, the output of that hashing algorithm will always have the same output size. The initial data is called the message, and the outcome of a hashing algorithm is called the hash or the message digest. So when I mention a hash or a message digest, that's the output of a hashing function. A hashing is a one-way function, which means that you can put some input into that algorithm and you get your hash, but you can never return that hash back to the original input. It's a one-way only. Input becomes a hash. You can never ever reverse that, otherwise the hashing algorithm would be broken. So if we look at a small example, we have the hashing algorithm in the middle. The SHA-256 is a very commonly used hashing algorithm. And we have three inputs, dog, doggo, and a quick brown fox jumps over the lazy dog. They all have a different length, but the output is always going to be a hash of the same length, a 256-bit hash in this case. So no matter how big the input, output is always going to be the same. So it's going to be the same output for the same input. So no matter how many times you input dog, the output is always going to be the same hash. And it's a one-way function. You can never reverse that hash back to the original input. That hash, the first hash, you will never be able to reverse that back to dog, and so forth. It's a one-way function, and that's very important to remember. Some of the commonly used hashing algorithms are MD5. If you've been on the internet for quite a while, you might have used this in the past. We don't use it that often anymore. It's still good in certain cases, but it has a few flaws, and we mostly use the SHA algorithms these days because they're a bit more advanced than MD5 is or was back in its day. A variation on hashing is keyed hashing, which is basically everything that a hash is, everything that a hash does, plus something extra on top. And keyed hashes lets you validate the integrity and the authenticity of the content of the hash, which basically means that you can be sure that the input of the hash is what you expected it to be in the first place. And in order to compute a keyed hash, you need a key, a secret key. This is a password. If you see my talk about yesterday about passwords, I like passwords, but a key is basically a password. And if we take the same example again, we have our algorithm in the middle, our inputs on the left, and our outputs on the right. You still get a hash in the end of this algorithm. It's still going to be the same size, and it's still a one-way function. So that's everything we know from the hashing example before that. But we don't only use an input. Together with that input, we have that secret key that we're also going to input into this hashing algorithm. And depending on the secret used, the hash is going to be different for each input. So if I do the quick brown fox, etc., in a keyed hashing algorithm like hmax SHA-256, and I use the right secret on top, I get a certain hash. If I use the wrong secret, I get another hash. And just because I know the secret and I know the input, I can also know which hash to expect, so I can validate the integrity and the authenticity of that data. Some of the more commonly ones are hmax SHA-256, 384, 512, where the number is basically just the length of the output of that hash. But under the hood, they all work the same, just with bigger numbers. And some example use cases. I also mentioned this yesterday. Please don't store your passwords in plain text. We usually store them salted and hashed or keyed hashed in our databases. You can also use them for identifying big files. For example, you could use an index that's based on hashes of that file instead of looking through the whole file. You could use it for cache busting, database indexes, and blockchain. I will not talk about blockchain or cryptography, cryptocurrency in this talk. If you don't want to talk to me about that, please don't. But all of these principles are also used with cryptocurrencies and blockchain under the hood as well. So if you're interested in those technologies, this is still applicable to all of you. Cool. Hashing, keyed hashing. Next up is signing. Digital signatures offer all properties of keyed hashes, so everything that a keyed hash could do can also be done with a signature. Plus, they offer this very fancy term called cryptographic non-repudiation. And if you look this up on Wikipedia, it says non-repudiation refers to a situation where a statement's author cannot successfully dispute its authorship or validity of an associated contract, which is still a lot of fancy words for something that I like to call cryptographic non-repudiation can prove who created that signature. So signatures, whenever you see a cryptographic signature, you should be able to prove who or which system, which service has created that signature. And that's the extra piece of candy on top of keyed hashes, basically. There are keyed hashes in a big part of the sense, but you can also prove who created these. And with a keyed hash, you cannot, because anybody that knows your secret could potentially create a keyed hash that you expect to be valid. Cryptographic non-repudiation, it enables other parties other than the signer to check the signature's validity. Again, with keyed hashes, you use a secret, and in most cases, we don't like to share our secrets. So we need to find a way where we can let other parties, other people, other services validate the validity of our signatures. And this is often done, or this is always done, with public key cryptography, also known as asymmetric cryptography, where the signer will create a signature using a private key. So whenever you create a new signature, you're going to use a private key. And then if somebody wants to verify that signature, they can use the public key that is linked to the private key to check the validity of that signature. And since it's a public key, you're free to share that with anybody in the world. It's in the name public, it's public data, it's something that's free to be shared. You only need to keep your private key always secure to yourself. So you create a signature with a private key, and anybody can validate that signature with the public key. A signing algorithm is usually a few algorithms packaged as one. You need something that is going to generate the public and private key pair. You need something that is going to create the signature, so a signing algorithm, and something that will be able to use a public key to validate that signature. So it's usually at least 3 things packaged as one. And if we look at the same example, we have an input, we have a signing algorithm that takes a private key to create a signature, and we get an output. Now, most signing algorithms also are hashed inside somewhere in the algorithms, so you also get a fixed length with most signing algorithms. But what's good to know is you have the input, signing algorithm with a private key, and you get your signature. And then whoever wants to validate that can take that same input, run it through the can take that signature and run it through the verifying algorithm together with the original input, together with the public key, and then you'll know if the signature is valid or not, if somebody has tried to tamper with the original data or the signed data or not. And some commonly used public key cryptography approaches when signing are RSA, elliptic curve, and Edwards curve octet key pair keys. And the most commonly used RSA keys are RS and PS. These are two commonly used algorithms. And they're very fast to compute because they're relatively easy, which also means that they're relatively CPU friendly, and they have quite a good support, especially RS because it's relatively easy. So most libraries start by implementing RS as a first signing algorithm. But to have a certain amount of security, a minimum of 2056-bit is recommended. You also need quite long keys, 2056-bit keys, which also means the longer the key, the longer the signatures. Elliptic curve keys, they require shorter keys for the same amount of security, which means that you get shorter signatures, but they're a bit more complex, so they're a bit harder to compute. And Edwards curve octet keys are basically the best of both worlds. They have the best signing performance for the same kind of security, but they're relatively new and not all libraries have support for them, and they're also not as easy to understand and implement as, for example, RSA. But some example use cases, JSON Web Tokens are usually signed. You also can use a key hash for JSON Web Tokens, but we recommend using a signature instead of key hash because of that cryptographic repudiation, because it works with a public and private key pair instead of a shared secret. But a JSON Web Token can be signed, or you can use a key hash. And when you want to sign a document online, for example, you will also create a signature, a cryptographic signature based on the input of that document. Cool. Hashing, signatures, encryption. This is the last step before we can move on to the actual HOSE specification. And when encrypting data, we can not only ensure its integrity and authenticity, just like with signatures, we can also ensure that it's what we think it is, but also the data will stay secret for outsiders. In theory, nobody should be able to get to the actual encrypted data except the person, the service, the instance that you would like to get to that data. So what you need is either a private key, a secret key, or a password, depending on the algorithm you're using. And the encrypted message is often called a cipher. When I speak about a cipher, it's the end result of an encryption algorithm. And you have two kinds of encryption, symmetric and asymmetric encryption. Symmetric one is the most simple one. And we use this when we want to encrypt large pieces of data, because it is a bit more simple as asymmetrical ones. When we need to encrypt a huge chunk of data, we usually use a symmetrical algorithm. For example, when you want to encrypt a whole file system, a whole database, or a lot of network traffic, you might want to use a symmetrical algorithm. And they're simple as in they use the same shared secret to do both the encryption and decryption, which makes them a bit more easy to implement as well. It makes them a bit faster because you don't have to rely on a public and a private key pair. You just have that shared secret to both the encryption and decryption. So if you know that secret, you can create ciphers, and you can also decrypt those ciphers again with the same shared secret. On the other hand, asymmetric encryption uses a public and private key pair, where it will use the public key to create an encrypted message. And this is a mental shift from signatures, where you use a private key to create a signature and use a public key to validate this. When you want to encrypt a message with a public and private key pair, you use the public key to create the encrypted message, and you then send that encrypted message to somebody that owns the private key that's linked to the public key, and they can use their own private key to decrypt the message. So it's a mental shift, for me at least, the other way around as signatures. So when you receive a cipher, an encrypted message, you can use your own private key that's linked to the public key that you send to whoever created your encrypted message to decipher, to decrypt that message. So in the same example, you see that when we encrypt a message, we use a public key, we get a cipher, and then if we want to decrypt that, we can use a private key to decrypt that message, and you can get back to the original message. This is different from signatures and from hashing. An encryption mechanism is meant to be reversed. It's meant to be so that people you want to read your data will be able to read your data. So this is a reversible algorithm if you have access to the public key and private key pair, or to the shared secret. Some example use cases: TLS, VPN, SSH. We see them all days of our lives. They all use a public and private key to do encrypted communications and so forth. And like I said, symmetrical algorithms are faster just because they use a shared key for a shared secret for both encryption and decryption, and that's why we use them with larger pieces of data. If we have smaller pieces of data, or at least data that we know the size of, we might choose a asymmetrical algorithm. So let's look at a detailed example. RSA, it's one of the more relatively easier algorithms to explain. And the first thing we need to do is generate the public and private key pair. And a small note, cryptography is usually based on algorithms that use very large prime numbers. And is a million a large prime number? Is a billion a large prime number? This is a large prime number, where this would be a million, this would be a billion, and I have no idea how to pronounce the name of this number on screen, but I think it's about 150 digits, and they can be even bigger, or they usually are even bigger in real-world examples, depending on which algorithm you use. So they use really big numbers, which means that they're really hard to brute force and to go through all of the numbers, all of the prime numbers between, let's say 0 and this number, or any of the available prime numbers above this. That's what makes them so secure. So when we create a public and private key pair, we're first going to generate two big prime numbers. 61 and 53 are prime numbers I chose for this example. They're not large prime numbers, but they're easier to see, they're easier to digest. So we generate two prime numbers, two unique prime numbers, random prime numbers, and based on these prime numbers, we also are going to generate a lambda value, which uses that mathematical function you can see on screen. So we have three values, three secrets, 61, 53, and 780, the first prime number P, Q, and the lambda value. And we only use these to generate the public and private key pairs, and after that we can forget about these. They're only used to generate the keys themselves. And the public key is going to contain the modulus and the public exponent, which the modulus is just the first prime number times the second one, and the public exponent is the coprime of the lambda. And the private key is also going to contain that same modulus, but instead of using the public exponent, it's going to use a private exponent, which is using that mathematical function on there. That's how RSA works. But basically, because we use the same prime numbers and that same lambda value to generate both keys, they're mathematically linked, and we will be able to use them in ways to encrypt and decrypt data. So if we use the public key to encrypt, we're going to encrypt the number 1234, run it through the RSA encryption algorithm together with the public key data, which is our modulus and our public key exponent. We get the cipher of 2183. Usually we don't deal with numbers, we deal with data in many types and forms, so you do have to do some data conversion. But under the hood, it's always going to be this mathematical algorithm that is going to take a number, an input number, run it through this mathematical algorithm together with the public key information, and you get some number out of that, which you can then transform back to the data format that you're expected. And if you want to decrypt that cipher using a private key, it's the same thing. You take the number, that cipher, run it through the decryption algorithm of RSA together with your private key information, and you get back to the original input, which is 1234. Again, you usually have to do some data conversion, but under the hood, it's always going to be that mathematical algorithm that's going to do some mathematical transformation on numbers using the public key or private key information, which are also basically numbers. And I recently, I think last weekend or 2 weeks ago, created a little playground that showcases more or less how this works for RSA. It's available on rsa.sambiga.tech, so if I type in a message, we get a decrypted or an encrypted message, and you can format this in many ways, however you like. But basically, this is the resulting number that comes out of that algorithm. And then at the bottom, you can see the prime number 1, prime number 2, the lambda function, or the lambda number, and so forth. And there's a small explanation. So if you're interested in how RSA works, I can link you to rsa.sambiga.tech, and I'll take you step by step in how RSA works. The same thing that I just tried to explain, but in a more visual way. Cool. Oh, I also have a GitHub repository that does more or less the same thing, but in your CLI. Jose. This is a talk on Jose, even though I've been speaking about cryptography for a long time. Cryptography and Jose, they go hand in hand. They deal with the same thing. Dealing with signatures, dealing with encryption on the web is Jose's job. So I mentioned this in the introduction. Jose stands for JSON, Object Signing and Encryption. And why JSON? The JSON format is often used for serializing and transmitting structured data over a network connection, which means that we use it on the internet a lot. I think most of us prefer it over any of the other alternatives like XML, YAML, all of those kind of things. Most of us like using JSON, especially in the JavaScript world, because, well, it came from the JavaScript world. And it has excellent support in most programming languages, especially JavaScript. So all of these specifications that are part of the bigger Jose specification are going to be JW somethings. JSON Web Tokens is the one thing that I already mentioned, but there's way more in those Jose specification than just JSON Web Tokens. The first one are JSON Web Keys. And this is going to be a JSON representation of public keys. So if we look at an example, this is JWK, a JSON Web Key. It's a public key in the form of JSON. And if you remember the little example of RSA before, we have our public exponent, and we have our modulus in there as well, the N and the E value, together with some more information about which algorithm we're using and so forth. But it's all just public key data in the form of JSON in a structured way, in a standardized way. That's basically what JSON Web Keys are. JSON Web Signatures is the next one. And if you've seen JSON Web Tokens before, this might look familiar, because most JSON Web Tokens are essentially JSON Web Signatures as well. And they consist out of 3 parts. When serialized as a string, you can also serialize them as JSON, which we'll see by the end of this talk. But most of the times we use them as a string, and they are serialized in 3 parts, and they're separated by the 2 dots in the middle, where the first part will be the Jose header, or the JWS header, which is a base64 encoded JSON object. Same goes for the payload, it's a base64 JSON object, and then you have the signature, which is a signature of that header and payload together. So if we decode that first part, we get a JSON object that tells us which algorithm to use to verify the signature. If we decode the payload, we get some kind of JSON. Any kind of valid JSON is fine. This can be strings, numbers, booleans, objects, arrays. As long as it's valid JSON, you can put it inside of that payload, base64 encode it, and you get a payload. And the signature is basically checking in that header which algorithm to use to verify the signature, and then inputting your header, your payload, and the shared secret, or the public key, depending on which algorithm you used to verify the signature, to verify that the payload is exactly what it should be. The next up is the most complicated one of all of these JW somethings, is JSON Web Encryption. And instead out of 3 parts, it consists out of 5 parts, where the first one will be the header, the second part will be the encrypted key, the initialization vector, the ciphertext, and the authentication tag. So it's good to note that the 4th part is the actual encrypted message here. All the rest are just side artifacts that we need to get to the actual encrypted message. That 4th part, the ciphertext, is the actual encrypted message. And JWEs use 2 kinds of encryption. I mentioned this before, we have symmetric encryption and we have asymmetric encryption. JWEs use both of them hand in hand, so it's basically double encrypted. So the content encryption key is usually encrypted with an asymmetrical algorithm because this is a short piece of data. It's a content encryption key which we're going to use to actually decipher the actual cipher. But before we can use that content encryption key, we also have to decode that, decipher that, and decrypt that to be able to use that. But it's a short piece of data, so we use an asymmetrical algorithm because they're more secure and it's fast enough to deal with shorter keys. So what we need to do is, the cipher is encrypted using a symmetrical content encryption key. So it's a symmetrical algorithm because we don't know how big the input of a JSON Web Encryption is going to be. This could potentially be a large chunk of data. So the actual cipher is encrypted with a symmetrical algorithm. The key to deciphering or decrypting that actual cipher is encrypted in itself with an asymmetrical algorithm. So let's look in the Jose header. The Jose header tells us a few things. It tells us which algorithms to use, and it also tells us which private key to use to decrypt the content encryption key. So if we want to decrypt that first content encryption key, the key we actually need to decrypt the cipher, we're going to look into the header, see that we need to use the RSA OAP algorithm, take a library that knows how to deal with that algorithm, and input the encrypted content encryption key together with the private key ID, of which the key ID is also mentioned in that header. And once we run it through that algorithm with the right private key, we get a decrypted content encryption key, which we can then actually use to decrypt the JWE, the JSON Web Encrypted cipher. So we look in our header again, we see that we have to use the A256 GCM algorithm in this case. So we take a library that knows how to deal with that, and we input the encrypted message, the cipher, the decrypted content encryption key, which we did in the first step, the initialization vector, which is a 3rd part of this string, which sometimes is just an empty string, and the authentication tag. And if you input all of those correctly, you would eventually get to your decrypted JSON web encryption thingy. So it's quite complex. You have a symmetrical encryption going on, you have asymmetrical encryption going on. You first have to decrypt your content encryption key before you can use it to actually decrypt your cipher. But if you do all the steps in the right sequence, you should be able to get to your decrypted message. And both JSON web signatures and JSON web encryption can be serialized as compact, which is the strings that I've showed you before, where JSON web signatures would be a string consisting out of 3 parts, and JSON web encryption would be a string consisting out of 5 parts. But they can also be serialized as JSON, because it's a JSON signing object and encryption standard after all. And this would be an example of a JSON web signature in the form of JSON. And this would be a JSON web encryption. And you can see that they contain all of the parts that we've talked about before. They have an initialization vector, they have the cipher text, the authentication tag, they have the header with all of the information. So it's still all in there, but it's just in JSON instead of as a string. And you might be wondering, when do I use which version? And the reason why we most of the time we serialize them as a string is because it's shorter, it's easier to transmit with a lot of requests, especially in the case of JSON Web Token. It's usually an access token or some kind of token that we have to send with each request to get access to our APIs. So we want them to be as short as possible to save on bandwidth and speed and time. So if you have to send them a lot, or if you have to send them over the network, you might want to choose to serialize them as a string. If you use them in other use cases and you use them more in a programmatic kind of way, you could do the JSON, because that's easier to read for us developers as well. Cool. Lastly, JSON Web Tokens. A JSON Web Token can either be a JSON Web Signature or a JSON Web Encryption. A JSON Web Token is always going to be serialized as a string. So the JSON serialization variants are not applicable to JSON Web Tokens, just because we use them as tokens, very often as bearer tokens. We send them over the network a lot. But both a JWS, which is the 3-part string, or a JWE, which is a 5-part string, could be valid JSON Web Tokens. 99.99999% of the time, they're the signatures, because they're easier to work with, and you should not put anything sensitive in that payload of a JSON Web Token. But if you do, and if you want to keep that sensitive data in that payload secure, you could also use a JSON Web Encryption for your JSON Web Tokens. It's just what I just said. And the only difference with when looking at a JSON Web Token is that usually in the header it also tells you the type, I'm a JSON Web Token. But apart from that, this is just a regular JSON Web Signature or JSON Web Encrypted message serialized as a string. And there's many forms of JSON Web Tokens, so we use them in many occasions. The most common one is an access token, which is going to be a token that's going to give you access to your APIs, that's going to give users access to certain API endpoints. So it only makes sense that the payload of a JSON Web Token access token is going to contain information that's related to that. So it tells you the issuer, which authorization server that issued the JSON Web Token, the audience, which is which API it has access to, when it's issued at, when it expires, which scopes it would grant access to, for example. So it's going to tell you all data that's related to accessing an API. If you look at an ID token, which is issued when you authenticate using OpenID Connect, it's an identity token, it's an ID token, so it's going to contain in the payload a lot of information that is related to the identity of the person that authenticated, things like my nickname or my name, maybe even my picture, together with, again, an expiry date and so forth. So, let's summarize before we can go and have lunch. Hashing compresses and makes it virtually impossible to get to the real data. It's a one-way function. The output is always going to be the same length depending on the algorithm. Keyed hashes do everything that a hash does. Plus it protects the integrity of the data because we use a shared secret, or maybe not even a shared secret, but it uses a secret on top of the hashing algorithm to get the output you desire. Digital signatures allow third parties to verify the validity and origin of data, just because they use a public and private key, and you can share your public key with anybody out in the world. So anybody that has access to your public key should be able to validate your signatures. For example, if you want to validate the signature of a Auth0 or any OpenID Connect conformant authorization server, they usually have a jwks.json endpoint somewhere on their API where anybody can go to and freely see all the public keys available to validate the JSON Web Tokens as signatures that are issued by that authorization server. Encryption allows only authorized people to read the data, so you will either need to have access to the shared secret, the password, or the private key that is linked to the public key that generated that encrypted message. And only if you have access to this kind of data, you will be able to decrypt the message and read the actual content. And Jose is a set of standards based on JSON that helps us deal with signatures and encryption on the web. These slides are available and will always be available on jose.sambigo.tech. JSON-WebToken.io is a website that I maintain at Auth0, where you can learn more about JSON Web Tokens, debug them, seed libraries, and so forth. The RSA demo example that I showed you earlier is available at rsa.sambigo.tech. It's still a work in progress. It doesn't work in Safari at the moment, I don't know why, but it should work more or less in Chromium and Firefox browsers. If you want to know how SHA-256 works under the hood, I would need about 5 hours to explain how that works because it's really complicated, but you have this website called SHA-256algorithm.com that basically shows you in a visual way how SHA hashes are made. So if I try to hash this message SHA and click on play, you'll see that it's going to do a bunch of computations over and over and over again to get to the actual hash at the end of this process, which would be here on the bottom. It's quite complex, but if you're interested, it's on SHA-256algorithm.com. Whoever made that website is a genius. That being said, thank you very much.
Really, thank you. Thank you so much for this talk.
Thank you for listening.
I didn't see any question on hoping, but perhaps in the room. Yeah. Run first.
I can hear you, but without it. Maybe the audience at home might need the microphone. Yeah, there we go.
Now it's working. Hi, thanks again for the talk.
You're welcome.
Amazing, as the last one yesterday. Very interesting. So I have 2 questions actually. The first one is concerning the cat on the screensaver.
Yep.
Is that the Nest.js cat? Just asking.
This one?
No, the other one, the one where you logged in.
No, that's my cat.
Okay, great. Nice cat.
I don't know if I can show you this cat.
Yeah, loved it.
That's my cat.
Is that a
But
Maine
thank you.
Coon?
It's a street cat. She's found on the streets, so she has no official race
Nice.
or
Love
type
her.
or whatever you call it, but she's my cat.
She's great. Now the other question, the one about the talk. So I've been using MSAL, SAML, OpenID Connect, all that kind of stuff as an end user. So I'm not very knowledgeable about it, but I had kind of to figure out a way for tree services solutions where you actually had to use MSAL2 library to connect to an Azure Active Directory, which could, with JVKS, verify with the public key the possibility that the signature was actually done by the end user.
Yep.
So, and that's okay, because that's like a two-way service, so you can bind it and you can know that it's verified. But at the same time, I would like another service, a third party, that I own, to be able to do the same verification, which would be possible if I was using something like Microsoft Online Common Endpoint, which I'm not, because it's Active Directory again. Okay. And using Active Directory, it creates a nonce that it uses to verify the end user. So is there some kind of way that this third-party service doesn't have to be actually connected to the main Active Directory to be able to use OpenID Connect and verify the signature by some kind of nonce verification mechanism or something?
There is no such thing as nonce verification because nonce is just a random value, which helps with verifying, but it doesn't do verification in itself. I am not familiar with your current architecture or with Active Directory per se, but if they have a valid OpenID Connect implementation, they should have a .well-known/OpenID Connect endpoint that is open for everybody. It should not be a protected endpoint, and in that is a JSON file where you can find basically the JSON web keys, the public keys, endpoint to see which JSON web keys they can use. So if it's an OpenID conform implementation that you have in your Active Directory implementation, whatever, that should be open and any service should be able to consume those JSON web keys. but I'm not familiar with your
No,
current
no, of course,
architecture, so
it wasn't like a consulence question.
Yeah.
It was more like, is there a way for, nonces are private to the service, right? So how would a third party that doesn't know anything be
Yeah.
able to actually verify something with a public
no,
key? That
yeah, I don't think there's a way. to
there's
do
no
that.
way out of it, right?
No,
Okay.
I don't think so.
That was the question. Okay, thank
Okay.
you.
No more question?
We all want food.
No, it's time to have another talk before the lunch. We are squeezing the lunch. No, I'm joking. I'm joking. It's time to have the lunch.